A very common struggle for folks is when they're working through chapters 9 and 10. They find that it's fairly clear in the individual sections what they need to do, but when they're confronted by problems that are stripped of context, they find that it's very hard to read from the problem what test or what confidence interval is required. So in other words, when you're in section 10.2, it's pretty clear that everything is going to be using a z-test. And when you're in section 10.3, it's pretty clear everything is requiring a t-test, and so on. But when you're confronted by problems that are free of context, or relatively free, like the ones you find in section 10.6, or the ones you find in the chapter review, or the ones you find on the exams, it's harder to know what test is called for. And so we'd like to use some examples here to help shore that up, and maybe it'll make you better at reading these. If you have your text, please consider joining me on page 568, and I have some problems that I'm going to take from section 10.6 here. First up is number 13. It says, smarter kids. Does playing Mozart for unborn babies result in children with higher IQs? A psychologist obtains a random sample of 20 mothers in the first trimester of their pregnancy. The mothers are asked to play Mozart in their house at least 30 minutes each day until they give birth. After 5 years, the child is administered an IQ test. We know that IQs are normally distributed with a mean of 100 and a standard deviation of 15. If the IQs of the 20 children in the study result in a sample mean of 104.2, is there evidence that the children have higher IQs? Use the alpha equals 0.05 level of significance. Well, clearly this is a test regarding a population mean, which kind of narrows it down a little bit. It's either a z-test or a t-test. And usually the deciding factor for a z-test is if they tell you the population standard deviation, which they did in this case. They told you that IQs are normally distributed with a mean of 100 and a standard deviation of 15. That's the population standard deviation. So if you were testing this question, that would be a z-test. And we can quickly run the test here. Summary statistics. Mu naught would be 100 in this case. Let me go down to that. Sigma is given to be 15. X bar is 104.2. Sample size was 20. And we're asking in this case, is there evidence that the children in the study have a higher IQ, which means that our alternative hypothesis would be mu greater than mu naught. It's a right-tailed test. And you can see right there from the p-value that the evidence does not support the alternative hypothesis. So in other words, the evidence we have is not sufficient to support the claim that these children have higher IQs as a result of being exposed to Mozart when in the womb. Next up we have question number 14. And the question says, atomic bomb. In October of 1945, the Gallup organization asked 1,487 randomly sampled Americans, do you think we can develop a way to protect ourselves from the atomic bombs in case other countries tried to use them against us? With 788 responding yes. Did a majority of Americans feel that the United States could develop a way to protect itself from atomic bombs in 1945? Use the alpha equals 0.05 level of significance. Well, you know, a majority is greater than 50%, and it's clear in this particular case that we're talking about a population proportion. So the correct test for this question would be a 1 proportion z-test. It's test number 5 here on this menu. And so let's go and take a look at that. P naught would be 0.5, that's 50% or a majority. X would be, in this case, 788. That was the number of people who responded yes. And the sample was 1,487. And it's asking, did a majority of Americans, so in other words, the alternative hypothesis would basically be what you see right here, P greater than P naught. And so we might want to make sure that we're firm on that, and then we can calculate. And the p-value is right here. You can see it's 0.01, and since the p-value is less than alpha, we would reject the null and we would say yes, it's clear that a majority of Americans felt that way. Take a look at number 15. Number 15 says yield strength. A manufacturer of high-strength, low-alloy steel beams requires that the standard deviation of yield strength not exceed 7,000 pounds per square inch. The quality control manager selected a sample of 20 steel beams and measured their yield strength. The standard deviation of the sample was 7,500 psi. Assume that the yield strengths are normally distributed. Does the evidence suggest that the standard deviation of the yield strength exceeds 7,000 psi at the alpha equals 0.01 level of significance? Now this is a chi-squared test. That's the test we use when we're testing claims about population standard deviation or population variance. And so in this case, the calculator doesn't have a built-in test, but it's almost built in if you know how to use the chi-squared distribution from the distribution menu. So the first thing we would need to calculate here would be the test statistic, which would be the sample size, 20 minus 1, so that would be 19. And then if you recall the construction of the test statistic, you're supposed to take sample standard deviation, divide by sigma naught, square the quantity, and then that's your test statistic. So in this case, sample standard deviation was 7,500, and we would divide that by sigma naught, which is 7,000, and we're going to square that. Now, this is a right-tailed test. The key sentence in the problem right here is the one that says, a manufacturer of high-strength, low-alloy steel beams requires that the standard deviation of the yield strength not exceed 7,000 pounds per square inch. And obviously the quality control manager thinks that they do, because he's got a sample with a 7,500 psi standard deviation. So in this case, your alternative hypothesis would be sigma greater than 7,000, and we can test that using a right-tailed test. It's perfect for chi-squared CDF. So this right here is going to be our lower limit, and to get our p-value, which is really all we need here to test this, we would go to the distributions menu. Number 8, you can't see it here, but if you scroll down a little bit, it's right there. Number 8 is the chi-squared CDF, which is the one we want, so I'll just press 8. And if you recall, the arguments it is expecting are lower limit, upper limit, and then degrees of freedom. So in this case, we're going to use the answer memory register for our lower limit. That's the test statistic we just computed. The upper limit would be positive infinity. Just use that as a proxy. And the degrees of freedom would be 19. And so we're calculating the p-value here. And since the p-value is so large, we cannot reject the null in this case. And the evidence that we have, even though it may seem so, it does not suggest that the standard deviation is out of spec. Next up, I got number 16 here. Number 16 says auto insurance. According to the Insurance Information Institute, the mean expenditure for auto insurance in the United States was $774 in 2002. An insurance salesperson believes that the mean expenditure for auto insurance is different now. He obtains a random sample of 35 auto insurance policies and determines that the mean expenditure to be $735 with a standard deviation of 48.31. Now, it's clear that this is a test regarding a mean, so it's either a z-test or a t-test. And this is the type of problem here that causes a lot of people to stumble. It seems that many people on the test would do this using a z-test. But it's not reasonable to use a z-test, because if you read the structure of the sentence, it's clear that all of the references are to the sample. It says he obtains a random sample of 35 auto insurance policies and determines the mean expenditure to be 735, that's x bar, with a standard deviation of 48.31. That's the sample standard deviation. It's not the population standard deviation. So this is a t-test, and the key sentence here is there enough evidence to conclude that the mean expenditure for auto insurance is different from the 2002 amount? That's a two-tailed test. So to run this, we go to the stat menu, go to tests, hit number 2, that's the t-test, and we input the following. Mu naught would be the figure from 2002, that would be 774. X bar is given in the problem, it's said to be 735. S of x is the sample standard deviation, it's given to be 48.31. N, sample size, would be 35. And like we were saying, it's a two-tailed test, so the alternative hypothesis is mu not equal to mu naught. We can then calculate, and with our p-value right there, which you can see is very small, it's given in scientific notation format, but if you were to write it as a decimal number, it would be 0.0003346, blah, blah, blah. In other words, 4 zeros in front of that 3 there. That's a very small p-value, and so we would naturally reject the null. And the evidence does suggest that the expenditure for insurance is different. It's changed. Number 17. Number 17 says mortgage rates. In 2001, the mean contract interest rate for a conventional 30-year fixed or 30-year first loan for the purchase of a single-family home was 6.3%, according to the U.S. Federal Housing Board. A real estate agent believes that interest rates are lower today and obtains a random sample of 41 recent 30-year conventional loans. The mean interest rate was found to be 6.05% with a standard deviation of 1.75%. Now again, it's clear from the grammar of this that we're talking about a test for the mean, first of all, so it's clearly Z or T. But the information we have here is based on the sample. They're not telling us the population standard deviation. They are telling us the sample standard deviation. It says the mean interest rate was found to be 6.05% with a standard deviation of 1.75%. That is sample statistics. It's not for the population. So this is also a t-test. And the key sentence here is that the real estate agent believes that the interest rates are lower. So this is let's run this test. It's a t-test. Number 2, summary statistics. Mu naught in this case would be 6.3%. So you can just put in 6.3. There's no need to convert it to a decimal. X bar would be 6.05%. So again, just key it in like that. S sub x given to be 1.75%. Sample size given in the problem to be 41. And it's a left-tailed test. Again, the key sentence being the real estate agent believes that the interest rates are lower. So he's saying basically that mu is less than mu naught. So there's our alternative right there, and if we calculate, we've got a p-value of 0.18, as you can see right here. Since the p-value is larger than alpha, we cannot reject. The evidence does not support what the real estate agent is saying. Number 18, I'll pass on that one. Let's see here. Final problem, number 20. Number 20 says toner cartridge. The manufacturer of a toner cartridge claims that a mean number of printouts is 10,000 for each cartridge. Consumer advocate is concerned that the actual mean number of printouts is lower. He selects a random sample of 14 such cartridges and obtains the following number of printouts. Now you can look at part A, and they're just asking us to verify normality, and everything looks fine there. So it's normal enough for us. And for part B, it says, are the consumer advocate's concerns founded? Well, what are his concerns? He believes that the mean number of printouts is lower. So in other words, this is a what test? A z-test or a t-test? Clearly it's for a population mean. Well, if you scour that right there, you cannot find a standard deviation anywhere. So they certainly haven't told us a population standard deviation. And since they've given us the data, they're figuring we're going to get the sample standard deviation from the data. So this is a t-test. So let's go back to the, quit that there, go back to the stat menu. Go to tests. It's number 2. We're using data. And mu naught in this case would be 10,000. So I'll key that in. Data's in list 1. You can see I've already got it keyed in right there. Frequency is always 1. And our alternative hypothesis is mu less than mu naught. And if we calculate, there we go. P-value is greater than the level of significance. Actually, p-value wasn't, the alpha wasn't given in, oh, it was at the very end right there, so it's higher than alpha, so we cannot reject. Anyway, this is something you guys need to practice. I hope this video will help you, so please find other problems in the book, practice, and check your answers.